I'm really surprised to see so many students here, and I'm also surprised to see some of my colleagues here. Thank you very much. Thank you very much. Thank you very much. Yes. Yeah, I'm pretty sure, pizza will taste better than my talk. So, and I just made the slides for you last night. So because, well, I have been talking about this at quite a couple of conferences, but because this talk is kind of targeted at, many say first or second year graduate students. So I modified my slides significantly, and I tried to make it hopefully as accessible as possible. And it's not really going to involve, say, any technical detail, I guess. But I will just try my best to give you guys an overview of, say, the research I have done in the past years and the research I may want to do in the next couple of years. And I guess the most important thing is that I just want to say,
no,
so I definitely need to want to graduate, at least want to graduate students to work with me on these MCMC research projects. That's kind of the main reason why I registered for this cafe and chose to give this talk.
First, I want to give a little bit introduction of you for people who don't know you. So Dr. Zhou is our assistant professor in our department. He started working in 2019. Did his PhD from Baylor College of Medicine in biostatistics, right?
Yes.
Did a postdoc in Rice University and has been published in very prestigious papers and conferences such as Journal Annals of Statistics, Neurips, AStat. So we welcome you. Thank you for being the first speaker of our Stat Cafe series this year. Pizzas are coming, and anyway, I think everyone will enjoy his talk, even the topic. Thank you.
Thank you very much for the introduction. Thank you very much for organizing this Stat Cafe. I'm really happy to be the first speaker this semester. Although at the same time, I also feel a lot of pressure. I will try my best to give an accessible talk. So as the name suggests, well, today I will just briefly talk about, say, the MCMC research I have been doing in the past years. So first of all, what is MCMC? So MCMC stands for Markov chain Monte Carlo. It's a class of sampling algorithms. So I know that sampling has many different meanings in statistics. For example, you may think about, say, the survey sampling. So you are standing in front of a blocker and asking every student passing by, what is your favorite class? Who is your favorite instructor? And the survey sampling is not going to be the sampling I'm going to talk about here. So the sampling problems I'm going to talk about, well, the setup is as follows. So let's say that you have, say, a target probability distribution pi. So here, by slight abuse of notation, you can think of it as a probability measure, or just think of it as a probability density function, whatever is kind of more comfortable with you. We assume that this pi is already given up to a normalizing constant. And then what I want to do is just to generate, say, I want to draw real numbers or maybe real vectors from this probability distribution pi. And the main idea of the so-called MCMC sampling is that we simulate a Markov chain, which is just a stochastic process with some particular structure. And then this Markov chain, we say that its stationary distribution. We say that this Markov chain is constructed such that its stationary distribution coincides with this pi, with my target distribution pi here. And now, for most Markov chains that satisfy some regularity conditions, if we have this property, then I can just write computer code to simulate this Markov chain. And if I can really simulate for an infinite amount of time, then the samples I'm going to collect, say, from simulating this Markov chain can be used to approximate, say, my target distribution pi. So this is the main idea of the MCMC sampling. So it's mainly about coding. So you write code to simulate the Markov chain, and you design your Markov chain in such a way that the output can be used to approximate whatever pi you are interested in. And the most important examples is probabilities in Metropolis-Hastings algorithms and Gibbs samplers. Actually, it gives samplers in particular, I mean, random scan gives sampler is just a special class of Metropolis-Hastings algorithm. So probably it's fair to say that most of the MCMC algorithms we have been using in the past, let's say 70 years, or maybe more than 70 years since Metropolis published his paper in 1953, they are more or less just all kinds of variants of Metropolis-Hastings. So Metropolis-Hastings is the framework, is the underlying framework for most of the MCMC algorithms you learn in the Bayesian course or you see in the literature. And why MCMC is useful? This is because in the Bayesian statistics, we often need to try to approximate some distribution, which we call the posterior distribution. And these posterior distributions involve the intractable normalizing constants. So what I mean here is that let's say I know pi x is proportional to a function fx, and I can evaluate this function fx. However, I don't know the normalizing constant here. So if fx is a density function, then you'll know that if I calculate the integral, it should integrate to 1. Right? So this means that well, if I want to convert this f to pi, then I only need to solve say this equation. Say the integral of the c fx should be equal to 1. And then if I solve this equation, I will get this constant c. This is what we call the normalizing constant. It's the normalizing constant which makes this function, integrate to 1, and then you can interpret as the probability distribution. But in Bayesian statistics, very often this C is not really tractable, so we cannot find what's the value of C. We cannot even say numerically calculate or approximate this function, this constant C. And then in these cases, you can always use the MCMC sampling because MCMC sampling only requires the knowledge of F instead of the knowledge of pi. So MCMC doesn't require, say, the knowledge about the normalizing constant. This is basically why it is kind of the main computational driving force behind the Bayesian statistics. And before I talk about, say, the sampling in detail, I also want to make a point that the sampling is actually closely related to optimization. This is, so some of you, well, I guess most of you know Michael Jordan, I mean, one of the biggest names in our field. I think in the past years, Michael Jordan and his group, they are really trying to kind of promote this idea that the sampling and the optimization, they are closely related to each other. So if you have a sampling algorithm, you can probably treat it as a stochastic optimization algorithm and use it for the optimization problem you want to solve. At the same time, if you have an optimization algorithm, then you can probably just modify it a little bit to use it as a sampling algorithm. So this is and this kind of analogy between sampling and optimization, I guess, has been studied a lot in the past, maybe 5 to 10 years, and there are a lot of, say, great research papers coming out. I mean, in both statistical journals and many conference proceedings. So even if, let's say, you are interested in optimization, then probably, I mean, it also helps, to learn a little bit about sampling. And I guess another point I want to make is just that, well, sampling is kind of one of the most fundamental computational problems in data science. Okay. And here I'm just plotting a toy with a bimodal example. So let's say this is my pi. This is the density function I'm interested in. And we call it a bimodal because we have 2 modes here. And if you do optimization, say, do some greedy search and you start from -4, well, I guess we can just think about the most naive optimization algorithms, which are deterministic, then probably you will just get stuck at the numbers in -2. And if you start from, say, +4, then you will probably quickly find this +2, and then you will get stuck. And if you do sampling, it's going to be pretty similar. So the main difference between sampling and optimization and the deterministic optimization algorithms is that for sampling, no matter where I'm currently at, there's always some small probability that I may go to the left, and there's always some say probability I'm going to the right. Okay. However, because eventually the goal of my sampling is to kind of recover this distribution. So the overall tendency of the sampling algorithm is still to move to where move to the high posterior regions. I mean, move to these 2 modes. So if I start from -4, then the sampling algorithm will probably also quickly arrive at this region around the -2, and it will probably stay here for a very long time. But if you really but if you can run this sampling algorithm, just forever, then probably it will eventually say, escape this area and then arrive at say the other mode. So that's just kind of the analogy between sampling and optimization. And the next, I would like to say just give you a couple of examples which I personally am very interested in, and these statistical questions kind of motivate say the sampling algorithms say I have been researching on. The first example is called variable selection. Most of you already know this. It's just another name. It's just sparse linear regression. So y is equal to z beta plus epsilon. Here I'm using z because I'm reserving the letter x for some other purposes. So this z is just my data matrix, n by p matrix. N is the number of observations, p is the number of variables. And variable selection means that, well, we kind of assume, well, most entries of this beta, this regression coefficient vector beta are equal to 0. And my goal is just to identify which entries of beta are not equal to 0. So my goal is to recover or to estimate this parameter gamma. Okay. I apologize. So this should be beta k equal to 0. Okay. So if this is my problem, then I can, well, I guess one way to attack this problem, one Bayesian way to attack this problem is just to, well, come up with some prior on this gamma and on beta, and then you just, well, write down try to figure out what's the posterior distribution of this parameter beta. And once you figure out the posterior distribution, which we denote by pi, then you can use MCMC to approximate this posterior distribution pi. And here, the search space, by search space, I just means the space that I'm going to run my MCMC algorithm on. So the search space is just going to be the parameter space of this parameter gamma. So this is just the set of all possible subsets of 1, 2, 3, blah, blah, until p. And if we consider, well, how many possible subsets there are, then the cardinality is simply given by 2 to the p. So you'll see that it is exponential in p. Okay. So the state space is very large. There are 2 to the p possible models. So obviously, if p is very large, I cannot enumerate all the possible models here. So in this case, you can just think of MCMC as some kind of stochastic search algorithm defined on this space and trying to figure out, what models are more likely. And for some of you who are familiar with the high-dimensional stuff, then you know that in high-dimensional settings, we will definitely introduce some sparsity constraints. We don't really want to conduct this search on the original model space, which has 2 to the p models. I will introduce some sparsity constraints. For example, I will assume, say, at most, there are only, say, 10 covariates that are related to my response variable. But in most cases, at least for most problems, we are interested in theoretical or applied problems. We are interested in, even after we introduce the sparsity constraints, then this model, then the search space, the number of possible models will still grow super polynomially in P. Okay. And here, well, if you kind of get confused, that's because in the variable selection, so you can introduce maybe a sparsity parameter, say S, and this is the maximum number of the covariates which may be associated with Y. In the high-dimensional settings, we want to let this S also go to infinity. So this S is not going to be fixed. If it is fixed, then it becomes polynomial in P. But we let it go to infinity. So it also grows with my sample size. This is why my state space, the cardinality of my state space is still super polynomial in P. Okay. And this super polynomial is kind of important here. So I try to highlight this because if you think about it, say the algorithm, no matter say sampling or optimization algorithms we use for these variable selection problems, then these algorithms are almost always local, where local means that in every iteration, I'm only looking at a very small neighborhood, and the size of this neighborhood is only polynomial in P. So what do I mean here? I mean, so no matter whether you want to do optimization or sampling, I guess a naive approach is just to, to begin with some initial random guess, say maybe the null model, which doesn't include any covariates, and then you just try to explore locally, and you decide whether you want to add a covariate or remove a covariate. So you consider these only local moves. And then you think about it, say how many models you can move to in the next iteration. This number is usually only polynomial in P. For example, you only allow, say, adding one covariate or removing one covariate. Then in this case, the neighborhood is just, the size is just a P, so it is polynomial. Okay. So why do I, okay, so before I comment on this, let me just give a two examples. I guess this is just a typical search path in variable selection. Say you begin with selecting covariates 1 and 2, and maybe in the next iteration, you choose to add maybe covariate 4, and then maybe in the next iteration, you do something which is a little bit more complicated, called swap, which means that, okay, I remove the covariate 2, and at the same time, I add covariate 3. And maybe next, I will remove covariate 4, and then I will remove covariate 1, blah, blah. So the point is that if you look at, say, every individual step, we are only making a very local move on the whole space. And then why do I want to emphasize the super polynomial and the polynomial? Because now you can see that it's entirely unclear whether my algorithm is going to have polynomial time complexity. So because if I don't make any assumption on, say, how this pi looks like, no matter whether you are thinking about optimization or sampling, then because the state space has cardinality super polynomial in P. And in each step, I can only look at, say, polynomial in many neighbors. So it seems that, it's quite likely that I need a super polynomial in many steps to be able to find where is the global optimum, or just to, confidently recover this whole distribution pi. Okay. So this is why we can ask the following theoretical question in MCMC. That is, okay, do we have any, say, polynomial complexity for the sampling algorithm? And also, if you think about optimization, you can ask similar questions. Do you have the polynomial complexity? Okay. These questions are not trivial because the state space is super polynomial. Otherwise, polynomial complexity becomes trivial. Okay. And this is just an example. So some of you may know this. This is GWAS. Means genome-wide association studies. This is kind of one of the major research areas in biostatistics in the past 2 decades, I guess. So it just means that I collect the genetic data of a lot of individuals, and I'm interested in understanding, say, what genes contribute, say, some particular disease. So I want to figure out what genes contribute, for example, to diabetes or to some kind of cancer. And this can be thought of as a variable selection problem. So your response variable is just the disease, say some cancer. And your candidate covariants are just, say, all these genes you have got, say, from this biological experiment. And of course, the number of genes can be very large, So for these problems, P can be much greater than your sample size. And so this is just a website called the GWAS catalog, and if you go to this website, you can find a list of almost all the results from the GWAS study. So you can just search, for example, lung cancer, colon cancer, and then you will see what genes, what genetic variants may be related to this cancer according to the statistical analysis. Well, and of course, very often by statistical analysis, I mean some variable selection methods. And you can consider some problems which are pretty similar to variable selection, but it can be even a little bit more challenging. For example, in biology, there's a question called heritability estimation. Here, I'm not going to explain what is heritability. I just want to kind of, statistically speaking, it just means that, okay, I'm doing this variable selection problem where I have, say, maybe, say 10,000 genes, and I'm interested in understanding, so what genes contribute to lung cancer. But at the same time, I also want to estimate, say, this quantity. So I also want to estimate, say, what proportion of the variation in Y is determined by these genes I have. Okay. And this looks like, an easy problem, but actually, if in the variable selection context, you want to do both variable selection and also, say, this estimation, the problem becomes a lot more complicated than variable selection. For example, for those of you who are frequentists, lasso, right? Lasso is not going to work, say, for this estimation problem. And there are some more complicated versions of lasso which are designed for estimating this. So you may think, I'm just trying to estimate, say, one single quantity, and it seems, say, much easier than selecting, say, what variables are correlated, but actually this is a very complicated problem. And I think the problem is particularly complicated when you don't really know, say, your signals are sparse or dense. Then you want to have some kind of adaptive method, which means that you are able to recover this quantity when there are only a couple of genes that are related to this cancer, or say most of the genes are related to this cancer. So you want to kind of recover, you want to be able to estimate this in both scenarios. But anyway, in the MCMC context, in the Bayesian methodology, I guess it's not really that complicated. You just write out a hierarchical Bayesian model, and then you do MCMC. And now when you do MCMC, in addition to sampling gamma, you also need to sample, maybe some error variance, or maybe just some other parameter which quantifies this thing. Okay. So this is things are often tend to be more straightforward when you formulate the problem in the Bayesian context. The next example is structured learning, which means that I want to learn a graphical model. So here by graphical model, I'm referring to directly the acyclic graph. Okay, so I'm not talking about the undirected model. Let's just think about DAX. Okay, and here the idea is that let's say I have NID observations. Okay, so essentially here I'm still having a big matrix. So, but I'm just and I call them NID observations. So each observation here is again a vector, say with p elements. Okay. And I assume they are ID, so every Z1, Z2, Zn here, they are drawn from the same probability distribution. But of course, it is a multivariate, it is a p-variate probability distribution. And my goal is just to figure out, say, what's the underlying DAG model that describes all the conditional independence relationships among these p variables, okay, among these p variables. So, so this is, again, you can call it a model selection problem, and you can formulate in a Bayesian way. So you put a prior distribution on all possible DAGs, and then you put some prior distribution on the parameters, and then you try to figure out what's the marginal likelihood for every DAG, and then you get a posterior distribution on the DAG space, and then you try to do sampling. So in this case, the search space where this pi is defined is the collection of all p vertex labeled DAGs. And how large is this space? It is going to be much larger than the previous variable selection problem. And actually, the number of p vertex labeled DAGs is super exponential in p. It is super exponential in p. You can actually do this calculation yourself, and there is an explicit recursive formula for calculating how many DAGs there are given p nodes. Actually, this number grows very quickly. Okay, when p equal to 8, it's already impossible to enumerate all possible DAGs, which might be a little bit surprising. Okay. When you only have 2 variables, of course the problem is easy. So here I just want to show the simplest case. So you only have 2 variables. Say I conduct some clinical trial and I observe whether someone has lung cancer or not, and I will observe whether someone smokes or not, and I want to understand the relationship between these 2 variables. So here p is only equal to 2, and then in this case there are only 3 possible DAGs. So the first DAG is the empty DAG, which means that the 2 variables are not related to each other. And the second DAG says that lung cancer causes smoking, and the third DAG says that smoking causes lung cancer. For those of you who have taken the course on DAGs, then you know that if I only have observational data, I actually cannot distinguish between DAG2 and DAG3. And if you really want to figure out, so all I can observe is that lung cancer and smoking are related to each other, but I cannot tell whether lung cancer causes smoking or smoking causes lung cancer, at least according to statistics. And if you really want to figure out which one is the cause, then you can do some so-called interventional experiments. So you just get healthy people, you force them to smoke and see whether they will get lung cancer, or you get some healthy people, you make them lung cancer and see whether they will smoke. So this is how you can figure out the causal relationship here. But anyway, it's we know that it's a simple problem. We know lung cancer only causes lung cancer causes smoking, not smoking causes lung cancer, not lung cancer causes smoking. But anyway, we are statisticians, so outside of statistics, we know nothing. We can only see the data, and I know nothing except my data. Okay. So and the last problem is the PDE learning problem. Let's say that I have NID observations. So each observation here is a pair of some expanded variable and some response variables, Z and Y. And I assume that Y can be written as FZI, where F is just some very complicated function with parameters theta plus some noise term. Okay. And here, in particular, I'm assuming this F is the solution to some partial differential equation. Then in most cases, unless you are working on those very classical PDEs, the PDEs, they don't have in most cases, PDEs don't have closed form solutions. So now in this case, if you take the Bayesian approach, it's easy to write down the likelihood because you just calculate, so what's the difference between yi minus fzi theta, and then you plug in your error distribution. But how are you going to evaluate this f? It's going to be very time consuming. In most cases, because maybe you just want to simulate, you want to numerically solve this PDE. Numerically solving a PDE is quite time consuming. Okay. So why do I want to also mention this problem? This is because this problem, although here I may assume theta is continuous, but even if this time, say I can do a stochastic search, I can do an MCMC on a continuous space, the problem is actually not that much different from the discrete case, because I cannot quickly evaluate this theta, and I definitely cannot, in most cases, find what's the gradient of this f. So even although this is a continuous space, let's say I'm currently at a theta, because I cannot evaluate the gradient, so I don't know in what direction the likelihood of this pi is going to increase. So it's still somewhat like a discrete search problem where at the current theta, I can just randomly grab some neighboring theta and see whether it results in a larger likelihood. I don't have the gradient information. So without calculating pi, I'm not able to tell so which thetas are more likely, which thetas are less likely. So this is why I also want to mention this problem. Okay, so and the next, the Metropolis-Hastings algorithm. I guess this is something standard, and here I'm just going to assume my state space is finite, and I write down my Metropolis-Hastings algorithm. For those of you who are not familiar with this, no worry about this. In particular, you don't need anyway. So let me try to explain it. So the idea is that I just begin at say a randomly selected initial value, and here I'm using x to denote these states. So this is why I didn't use x in the previous slides. And then now, say in every iteration, I just try to draw some neighboring states randomly, maybe with equal probability, and then I decide whether I want to move to say this neighboring state or not. If no matter what I propose, I always move to that state, then of course, this algorithm is not going to help you recover the posterior distribution pi, and it's not going to help you do optimization either. So the trick here is that after I propose the next move, I will decide whether I move to it with some probability. And this probability is calculated according to this AXY. So with probability AXY, I'm going to move to the next state. With probability 1 minus AXY, I'm just going to stay at where I'm currently at. So this is the main idea of the Metropolis-Hastings algorithm. Yes, so you can just think of it as a stochastic search problem. So let's say that here, every dot represents a state, and the blue bars, the height of the blue bars represent my posterior probabilities. And I want to say approximately this posterior distribution by sampling. And let's say if I'm currently at x0, and these dotted lines just indicate that, well, which states I may move to in the next iteration. So I may move to x1, x2, x3, x4, x5, x6. I will just draw one of them randomly with equal probability, and then I will calculate my external probability and decide whether I'm going to move to that state or not. Because eventually, no matter whether you do optimization or sampling, you are always trying to find, those high posterior regions. You are always trying to find where pi is large. So arguably, you can say that at the point x0, the best move is x4, because x4 has the largest posterior, has the largest pi value. Okay. But now the question is, okay, is it really likely that I'm going to quickly move to this x4? Not really, because if I just do the random walk proposal, which was what I talked about a minute ago, then the probability that I'm going to propose x4 is only going to be 1/6, because there are 6 neighboring states. And you can argue that maybe 1/6 is a little bit too small. And actually, if you think about those high-dimensional variable selection problem, then proposing a really good neighbor, this probability can be exceedingly small. So this may seem a little bit undesirable. So what can I do? So I can use something called a locally informed proposal to increase this probability. Let's say that with probability 90%, I'm going to move to x4. With probability 10%, I'm going to move to one of the other states. Then this seems to be more efficient. And in the Metropolis-Hastings framework, you are allowed to do this. So, and if you do something like this, then you will arrive at just another Metropolis-Hastings algorithm, which here I call the informed Metropolis-Hastings algorithm. You can ignore this acceptance probability expression. The only thing that you may want to pay attention to is that, so I'm introducing this non-decreasing function h, and I'm assuming that I will propose a neighboring state y with probability proportional to h pi y over pi x. So this h will decide how much weight I put on each of the neighboring state. So this is the only thing that hopefully you can pay attention to here. And because I will come back to this h later. Okay, of course, this is a quite, straightforward idea. So it's not surprising that it has been used in a lot of papers and on MCMC, and also a lot of papers on non-MCMC methods. I think one paper here is written by our colleague and our previous student, Shane et al. I think it's written by Dr. Banachari and maybe Dr. Johnson. Anyway, so they proposed some non-MCMC stochastic search methods, and its main idea is quite similar to what I was describing. Okay. But one big disadvantage of this so-called informed proposal is that how can I really tell, which neighboring state is really the best one? Of course, I won't be able to tell this if I don't evaluate what is pi x4, what is pi x1, what is pi x2. So I need to calculate the pi x1, pi x2, pi x3, blah, blah. I need to evaluate the pi for all these neighboring states so that I'm able to tell which move is really going to be the best. So this is going to be very time consuming, right? Compared to the random walk. Random walk just says that I draw one neighboring state randomly, without any thinking, and that's pretty easy to do when you code it. But informed proposals, it's difficult. You want to first evaluate all the pi for all the neighboring states. But anyway, one argument frequently used in the literature is that this step can be easily parallelized. Well, I'm not going to comment on that. Because I think probably there are also other ways to use parallelization. But anyway, yes, you can do this in parallel. And the point I really want to make here is that, well, the Metropolis-Hastings algorithm is a very tricky algorithm, because even if you have a very strongly informed proposal, so you are always moving to, say, for example, with very high probability, let's say you always propose moving from x0 to x4. There's still one remaining question, that is this proposal going to be accepted? Because Metropolis-Hastings needs to calculate the acceptance probability so that, well, the samples generated from this algorithm can approximate the pi. And this acceptance probability in the informed Metropolis-Hastings framework can be exceedingly small if you don't really choose this informed proposal carefully. Okay. So it's very difficult to control this acceptance probability. And the informed Metropolis-Hastings algorithm can mix even more slowly than the random walk Metropolis-Hastings if you don't carefully select this informed proposal. So next, I'm going to ask 4 questions, and these questions are more or less, at least they were partially addressed in my previous works, and then you will see what are the future research projects we can work on. So question 1, do we have theoretical guarantees? So I said that informed MH algorithms, they are very time-consuming in every iteration, and they can be even more inefficient than random walk. Then do we really have a theoretical reason to use this informed MH? And more generally, we can also ask, do we have any theoretical guarantee for any Metropolis-Hastings algorithm, no matter what the proposal is? So the answer is yes. So in our paper, we developed some theoretical results which kind of justify, okay, so in some cases, you have, say, a polynomial mixing, you have a polynomial complexity guarantee for random walk Metropolis-Hastings, and sometimes you also have a polynomial complexity guarantee for informed MH. And actually, our theory shows that you can always find an informed Metropolis-Hastings algorithm such that its overall complexity is going to have the same order as a random walk Metropolis-Hastings. By overall, I mean that I already take into account, say, the computational cost in every iteration. And we also analyze the variable selection and the structured learning, these 2 examples in our papers. But anyway, so this is some theory. I guess I just want to quickly go over it. And next, let me move to perhaps more important questions. The next question is, do we have to use Metropolis-Hastings still? Okay. So as I said, in the past 70 years, most of the MCMC algorithms, they are based on Metropolis-Hastings. They are essentially Metropolis-Hastings algorithm. Okay. And my question is that, do we have to, say, really stick to this Metropolis-Hastings framework? And my answer is no. And actually, in many cases,
it can be much more efficient if you jump out of this Metropolis-Hastings framework and do something slightly different. And to introduce, say, the method we developed, I need to make a simplifying assumption that this function H is a balancing function, which means that it satisfies this property. You definitely don't need to remember what is this balancing property. It just means that this H needs to satisfy some algebraic condition. That's it, because this condition can simplify some calculations later. That's kind of the reason why we impose this assumption. But just to point out, actually, the class of the balancing function is pretty large, so there are many, many possible choices. And what's our solution? Okay, our solution is that I will always accept whatever is proposed. And of course, if I always accept whatever is proposed, then I look at what's the empirical distribution of my samples. It's not going to be pi. I'm just accepting whatever is proposed, right? But then if you have taken the Bayesian course, then you know that there's a famous sampling algorithm called importance sampling. If I know that the empirical distribution of my samples are different from pi, then as long as I can find out what's the importance weight, I can still use these samples to recover pi. And this is the main idea of the algorithm I'm proposing. I just accept whatever proposal is made, and I know that I'm not convergent to pi, and I will use importance sampling to correct for this bias. This is a very simple idea. And actually, if you look at, and if you write down the algorithm, it's also kind of easy. You just calculate, see, this proposal weight, h pi y over pi x for every neighboring state. And then if you sum them up, you get the importance weight. In our paper that, well, of course, one key observation here is that we prove the importance weight is pretty easy to get. You don't need to make any additional computational effort to get this importance weight. Okay. And of course, I personally think that this already shows that this could be more efficient than Metropolis-Hastings because you will never get stuck. Okay. But anyway, so just I definitely should give credits to Giacomo Zanella and Gareth Roberts. In their 2019 GSSB paper, they proposed something called tempered Gibbs sampler, which is very special, very complicated algorithm for the variable selection problem. But it is indeed just a special case of what I'm proposing here. But if you look at that paper, the presentation is going to be very complicated. And I think it's kind of really good to have a more general and simpler presentation of this algorithm. And next question, how can we choose the informed proposal? How can we choose this H? So I'm going to quickly go through these points because I think I'm running out of time. So I said that my only requirement is that this H is a balancing function, but there are many possible choices for the balancing function. And in Giacomo Zanella and Gareth Roberts' paper, they only consider the choice, say, HU equals 1 plus U. And in our paper, we show that actually, if you do this, say, informed importance tempering algorithm, which I proposed on the last slide. So if you do this IIT algorithm and you use HU equal to 1 plus U, yes, it is going to converge. I apologize, I forgot. This sentence is not complete. So it is going to converge extremely fast under some strongly unimodal assumptions. It's important. I mean, for whatever reason, apparently I deleted some important phrases here. So it converges extremely fast, only under some conditions. However, in more general settings, this choice is going to be too aggressive, and it can be very inefficient if your target is multimodal. And we show that the square root function actually probably performs much better in a very wide range of settings. Okay, so this is another kind of methodological question. Finally, is importance tempering really a general technique, or am I just proposing some algorithm which is very special and it cannot, say, be applied to many other, say, more realistic, complicated problems? So I guess the answer that our answer for now is that this technique is extremely general and it is widely applicable to almost whatever the MCMC scheme that you have seen in the literature. So in a paper I recently wrote with Quan here, so we showed that you can incorporate this technique into many complicated MCMC schemes. Some of you may know these terms like simulated tempering, pseudo-marginal. Anyway, these are fairly complicated MCMC schemes, but they can be integrated with this importance tempering technique I'm proposing here. And more importantly, we also show that there's an algorithm which is called the multiple try Metropolis algorithm that can be again revised to obtain, say, an algorithm similar to IT in the sense that you always accept the proposal. You move to whatever is proposed, and you correct for the bias by importing something. And this multiple choice version is applicable to whatever spaces you have. So even if you have a general state space, a continuous state space, you can still use this importance tampering idea to make sure that you always accept whatever you propose. And our numerics also show that it really converges much faster than the Metropolis-Hastings algorithm. Okay, I think that I will just use maybe 4 minutes to summarize, to briefly talk about what we can do later, so future research projects. So as you can tell, so I think I'm mostly done with the key theoretical or the methodological question here. So the next thing I want to do is that I want to do some really good computational research. So I want to develop, say, these IT-based MCMC algorithms for arguably, say, more complicated statistical problems, including those problems I have just talked about, for example, PDE learning, variable selection, structural learning, these things, and maybe heritability estimation. And I'm also very interested in the so-called stochastic neural networks. This is something developed by Fan Liang at Purdue University. So that can also be kind of integrated with, say, the Monte Carlo sampling algorithm, and it seems interesting because it's related to machine learning. So what are the potential challenges here? Although it seems straightforward, okay, so what I want to do is just kind of write the code. But personally, I think that there's always a really huge gap between proposing some algorithm and then really implementing it and really arriving at a complete solution for a practical problem. So these gaps are very large, and I think that it takes a lot of effort to really fill these gaps. So in particular, I think that when you write the code, so we want to make it efficient. And when you implement an MCMC algorithm, for example, for a variable selection problem, you want to be familiar with those numerical linear algebra techniques so that you are able to implement everything in an efficient way. And probably if you know CPP, then you can write an RCPP code which will run much faster than R. And these things are definitely not trivial. And it's quite complex. It's very interesting, and it involves a lot of I think interesting math. Okay. And also when we have a complicated problem, then you probably also want to consider a more realistic or more flexible statistical models, which may involve more hyperparameters, and then how to do sampling when you have more hyperparameters, when you have, say, maybe both discrete and continuous parameters. Can you really, for example, combine Gibbs sampling and the Metropolis-Hastings, and also the importance tampering method that I'm proposing here? So you will run into many challenges, but for most of them listed here, I think that I know how to attack these problems. For example, let's say I cannot exactly evaluate pi when I make this informed proposal. I only have some approximately informed proposal. Then can we still do something like this? Can we still arrive at a Markov chain which does converge to pi? Or how can we quantify the bias? Things like that. So I mean, it's definitely. I would still say it's quite challenging, but because I have been working on these computational stuff in my PhD, so I will be very happy to work with you on this computational stuff, writing the code. And the next question is that, which is slightly unrelated to what I talked about, is how can we estimate the MCMC convergence rate as we run this MCMC algorithm? And for this problem, I also have some ideas about how to attack it. It's still mostly computational because we want to do simulation, we want to implement the algorithm for different problems and see whether it works. But for this project, if you have a little bit knowledge about Markov chain mixing, then that will also be useful, but this is not necessary. And for this estimation of MCMC convergence, I believe that if we want to do it for the Metropolis-Hastings, then it will be slightly easier. But if we want to do it, for the IT versions I have proposed, because of the use of the importance weight, actually estimating the convergence rate may be a little bit more challenging. So there is some methodology to be developed here as well. And finally, eventually my goal is that I want to develop adaptive MCMC methods that can always work even for multimodal targets. So what do I mean by adaptive? It means that when you run this MCMC algorithm, you are essentially exploring the whole space. So after you explore this part, then you have some knowledge about it. And after you explore that part, you have some knowledge about it. Then you want to incorporate this knowledge into what you are going to do next. If you know that, well, the posterior is very low in this area, then probably you don't want to revisit this area.
This is what I mean by adaptive. But actually, you can do this adaptive MCMC in many possible ways. For example, how can we say adaptively partition my state space into multiple parts and then do a divide and conquer thing? And how can we say adaptively decide how much computational budget I want to allocate to every subset of my state space? And how can I adaptively learn the optimal informed proposal scheme? So I mentioned that we have that H, which is kind of one of the tuning function here. They can adaptively learn what's the optimal H here in this adaptive MCMC framework. So this is kind of the eventual goal of my research. But of course, this is going to be, I guess, mostly computational, because I would say that the development theory here is not very helpful and probably it's too difficult. Yeah, that's all for my, sorry, the one last thing. I just want to say that when we work on these things, I expect that you will be able to learn a lot of skills which can be very helpful to you no matter whether you go to industry or academia. For example, when you do the code, because we need to code the MCMC, so programming is of course the most important skill here. And as I said, because I personally really care about these implementation, like this numerical linear algebra implementation. So by working on these projects, you will also get familiar with these things. And of course, you will learn how to do statistical simulation. I think statistical simulation is something quite complicated, quite interesting, quite deep. So please don't just think of it as something very naive. It's much more than just writing a correct code and then do a simulation in whatever scenario you come up with. And of course, if you are interested in the theoretical part, we can also study a little bit about what is the MCMC convergence theory, and we can also even do a little bit, theoretical, do a little bit theory on the high-dimensional Bayesian statistics. In particular, for the heritability estimation problem I mentioned, I believe the Bayesian theory is not really developed there. And according to my personal experience, I found that the Bayesian method can automatically get adapted to the sparse level of your signals, but theoretically why it happens, I'm not very sure. And that's some theoretical question we can work on later. So that's all for my talk today. So yeah, thank you very much.
I have two questions. So let's say you want to apply the MCMC to the variable section, and we use the addition method. We have a high-dimensional family vector, and then we have some Excel samples. So I'm wondering, how do you determine if it converges to the target distribution for this high-dimensional variable?
In principle, it's important because it's always likely that you have only explored a very small part of the space. So if you just want a yes or no answer, then the answer is no. You will never be able to say with 100% confidence tell whether you have converged or not. Yes, but you can definitely try to do some diagnostics, and this is something that actually will be covered in your Bayesian course. You will see some MCMC diagnostics.
Because I know, for example, for the continuous branch, you can definitely observe the chip plot for.
But that's still not enough, because
in
theory you can just get stuck in a small area. So, but you can definitely tell, well, in the area that you have, in the regions you have explored, whether you have really mixed or not. And you have a bunch of techniques, like making a trace plot or calculating some statistics like German using statistical.
Any more questions? Yes.
Yes.
Has this been investigated at all when applied to a non-parametric Bayesian model?
Yes.
You might need reversible jump forward.
I definitely have only been working with really simple models for the non-parametric stuff. I haven't looked at that. Well, I probably should remember what I said. I mean, for example, the graphic model is extremely complicated.
More questions? Thank you very much again.